Hey guys, so at this point you should have read the article about what it means to be radioactive, and you should have some idea of what nuclear chemistry is going to be all about. So basically, if we say that something is radioactive, we mean that its nucleus is unstable. And because it's unstable, it's going to do something to change itself and try to get more stable. Just like in a chemical reaction, let's say an atom doesn't have a full valence shell. What is it going to do? It's not going to sit there and just be unstable. It's going to go bond with something to fill its valence shell and get stable. But since we're talking about nuclear chemistry, this is not an electron shell thing. We're looking at what it means for the nucleus to be unstable. So I'm gonna go out of this and show you guys an app. You can download it on your phone if you want. It's called Nuclear, and it's basically an app that lets you build atoms. So let's say I wanted to build a carbon atom, right? Can you guys go to your periodic table and tell me what carbon's atomic number is? Okay, so atomic number 6 means that I need 6 protons, and I also need 6 electrons because the protons and the electrons always have to cancel out. So if I just try to add 6 protons, see how nothing's happening? Why do you think 2 protons, there's already one there, why do you think 2 protons wouldn't want to be near each other? What charge does a proton have? Positive, right? And if you tried to put together 2 positive things, what would they do? They repel each other. They push away from each other. So I can't just go ahead and shove 6 protons in the nucleus. I have to do it kind of like one at a time. Here's a proton, here's a neutron. Here's a neutron, right? What is carbon supposed to weigh? Right? So if I have 6 protons, how many neutrons do I need to make it weigh 12? I need 6 as well. So I'm going to go ahead and do that. I'm going to add 1 of each. Okay, I'm going to keep ignoring that. And did I add something too many? Nope. Okay, so now I'm going to go ahead and put in my electrons until this has a charge of 0. Okay, and I've made stable carbon that has a mass of 12. Okay, I don't want to do this. I'm going to go back to my atom. Okay, so now carbon has an isotope. Carbon-14 is considered radioactive, and I want you to take a look at how we make carbon-14. We need to make it weigh 14 instead of 12, so we need to add something extra to it to make it heavier. Am I allowed to add protons? Absolutely not, because then its atomic number would change and it wouldn't be carbon anymore. But if I add 2 neutrons, that would make its mass go up to 14, yes? So let's add 1, 2. How did the symbol in the top right box change? See that little radioactive symbol, that little triangle? So what that means is my nucleus is unstable. And this is a new version of the app, so I'm not sure if it's going to do what I'm hoping it's going to do. Doesn't look like it. Okay, so what an unstable nucleus will do, that's when your proton and neutron ratio is not 1 to 1, when like the number of protons and neutrons is very different from each other. So what's going to happen is this atom is going to get rid of particles and turn into a totally different element so that it has a nucleus that's more stable. So if you guys wanted to play around with that app, it's pretty cool. All right, so there are 2 ways this can occur. The first is naturally, where you have an unstable atom and it gets rid of particles and it becomes more stable. Okay, so let's look at my first example. I have gold 198. So there's the mass right there. Whatever mass they give you, you have to use. But I want you guys to go to the periodic table and I want you to find gold right here, and its atomic number is 79, right? So when we do these equations, we not only need to know the mass, we need to know the atomic number. Okay. The next thing I need to do is figure out when this unstable gold decays, what particle does it get rid of? So table N is a new reference table that we've never used before. Okay, it's right here. And it gives you a whole list of nuclides. Those are like radioactive elements. And it tells you their decay mode. So gold 198 is the first element. And see in the decay mode column, there's a B minus sign. That means when gold 198 decays, it gets rid of a B minus particle. What the heck is a B minus particle? Another table that you need to do these questions is table O. Okay, so where do you see the symbol B minus? It's a beta particle. So a beta particle you can write two ways. I'm going to just pick the first way because that's where I see it. So I have the mass of the beta particle, the charge of the beta particle, and the symbol of the beta particle. Okay? So now you need to figure out, okay, well, when gold gets rid of this particle, it's going to turn into something new. What is it going to turn into? You have to think about conservation of mass and conservation of charge. The gold on this side weighs 198. So that means that these two particles, they need to have a mass of 198 together because the left side and the right side have to weigh the same. So if the beta particle weighs 0, what does my other particle have to weigh? 198. Okay. The bottom number is the charge. So gold has a charge of 79. That means that when these two particles get added together, their charges have to add up to 79. So the beta particle has a -1 charge. What plus -1 is going to equal 79? 80. So now that I have the mass and the nuclear charge of my missing element, I need to figure out what element it is. So that bottom number, the nuclear charge, that's the same as the atomic number of the element. So if I say, okay, I'm looking for element number 80, I'm going to go to my periodic table. I'm going to find element 80. There it is. It's mercury. And my new element that I've created is mercury. And what this means, guys, is that gold got rid of a beta particle and it turned into a mercury atom. It turned into a different element that was more stable. And this is called a natural transmutation because this happened all by itself. We didn't have to do anything to force it. Okay? Let's look at the second one together. Okay? Same steps, guys. Calcium, I have a mass for it. I need an atomic number. Oh, geez. I need an atomic number also. It's got atomic number 20, right? All right. Now I want to go look at table N. I want to figure out when calcium decays, what particle does it get rid of? So calcium 37 gets rid of a B plus particle. A B plus particle. Did you guys see that? I think my computer froze. So calcium 37, it's the third one from the top. See how it gets rid of a B plus particle? I go to table O and I find the B plus particle, which is right there at the bottom, and I write down its symbol. Again, it has two symbols, so it does not matter which one you write. Okay, so now how do I figure out what's missing? My top numbers have to add to 37. And my bottom numbers have to add up to 20 because this side is 37 and 20. Okay, so if the positron weighs 0, then this whole thing has to weigh 37. And if the positron is a 1, this has to be a 19 in order for them to add up to 20. So what's element number 19? If you go look on your periodic table, it is potassium. So calcium naturally got rid of a positron and turned into a more stable atom. So the protons and neutrons in this guy are closer to having a 1-to-1 ratio. Okay? So I left two for you guys to try. I will put the answers on the copy of class notes that I'm going to post, but I want you guys to try those yourself. All right. The next type of transmutation is artificial transmutation. And when I see that word artificial, it sounds fake, right? And that's exactly what this is. This is something that's fake. It's forced. These nuclei are stable. If things are stable, they don't want to change. We can force them to change, but that's why this is called artificial and not natural. So what we do is we take this nucleus that's all good, it's stable, and we bombard it with another particle. We throw a particle at it and try to mess up the nucleus and change it into something new. So these are actually a lot easier to do because there's no reference tables to worry about. They're going to give you the stable nuclei, and they're going to give you the particle that we hit it with, and you just have to figure out what did it turn into. You're using, guys, the same technique as before. The masses and the charges on the left side and the masses and charges on the right side have to be the same, okay? So what's my mass over here? 14 and 4 is 18. So my masses have to be 18 over here as well. My charges over here, 7 and 2 is 9. So my charges over here also have to be 9. Okay, so now I can figure out what my missing piece is. If my top numbers have to add up to 18 and hydrogen is already 1, this has to be the 17. If my bottom numbers have to add up to 9 and hydrogen already has a 1, then this has to be 8. Which element has an atomic number of 8? Oxygen. Okay, so they're going to give you everything and just one thing is going to be missing. We'll try this next one together. Masses add up to 10, so the masses over here have to add up to 10. The charges over here add up to 5. The charges over here have to add up to 5. Okay, so helium's got a 4, that means I need a 6. 6 and 4 is 10. Helium's got a 2, that means I need a 3. 3 plus 2 is 5. What's element number 3? Lithium. Okay, so these are not that bad because you don't have to look anything up. How do I know it's artificial? Just by looking at it. You can see, guys, there's two reactants. There's the element and then there's the particle that you're hitting it with. Where in natural transmutation, there's only one reactant. It decays all by itself. It doesn't need to get hit with anything. So this practice one, I want you to try by yourself. I'll post the answer to it on the copy of class notes. Okay? In summary, what's the difference between natural and artificial, guys? So again, natural is one reactant, and artificial is two reactants. And why is it only one reactant? Because it happens spontaneously. It decays all by itself. So natural is spontaneous and artificial is not spontaneous. What do they both have in common? In both of these cases, if you looked at the left and the right side of the arrow, transmutation means you're turning into different elements. Okay, which really leads us into this last question, guys. I want to know how nuclear reactions are different from chemical reactions. This is an example of a chemical reaction. Do you see the same elements on both sides of these arrows or different? You absolutely see the same elements. You see hydrogen and oxygen on both sides of the arrow. So chemical reactions have to do with bonding with the same elements. So you're always going to have the same letters on both sides of the arrow. They're just going to be put together different. With nuclear reaction, there's always going to be different elements on each side of your arrow. Okay, so that's it, guys. Once you're finished with the practice, you can check your work, and then we posted another Castle Learning to help you guys practice this. All right, have a good night.